Physicists of the early 1900s also were challenged by another troubling experimental result that could not be explained by Maxwell's wave theory. When ultraviolet radiation was incident on a negatively charged zinc plate, the plate discharged. When ordinary visible light was incident on the same charged plate, the plate did not discharge. This result was contrary to electromagnetic theory. Both ultraviolet radiation and visible light are forms of electromagnetic radiation. So why would the zinc plate be discharged by one but not by the other? And why would a positively charged zinc plate not be similarly discharged? Further study showed that the negatively charged zinc plate was discharging by emitting or ejecting electrons. The emission of electrons when electromagnetic radiation falls on an object is called the photoelectric effect. The photoelectric effect can be studied in a photocell, such as the one shown. The cell contains two metal electrodes sealed in a tube from which the air has been removed. The evacuated tube keeps the metal surfaces from oxidizing and keeps the electrons from being slowed or stopped by particles in the air. The larger electrode, the cathode, usually is coated with cesium or another alkali metal. The smaller electrode, the anode, is made of a thin wire so that it blocks only a very small amount of radiation. The tube often is made of quartz so as to allow ultraviolet wavelengths to pass through it. A potential difference placed across the electrodes attracts electrons to the anode. When no radiation falls on the cathode, there is no current in the circuit. When radiation falls on the cathode, a current is produced, which is measured by the ammeter, as shown. The current is produced because the photoelectric effect causes the ejection of electrons, also called photoelectrons, from the cathode. The flow of electrons is the current in the circuit. The electrons travel to the anode, the positive electrode.